All right, let's take a look at another CSES math problem, another probability problem, in fact. Candy lottery, so what's going on here? There's n children, and each of them we randomly give a number of candies between 1 and k, right? So uniform, 1 and k. What is the expected maximum number of candies? We're given n and k, and we should output this to 6 decimal places. Okay, so there's actually a neat trick we can use here. Let's take a look. So here's the fact that we're going to show. If x is a random variable that always it's a positive integer, right? Those are the only values. Then there's a neat trick that we can use to calculate its expected value, right? So the definition of expected value is this, right? It's 1 times the probability that x equals 1, plus 2 times the probability that x equals 2, 3 times the probability that x equals 3, and so on, right? It's just the value times the probability of that value for all the different values. And this sum actually goes up to x equals k, right? Because the maximum can't be more than k. I mean, this is actually true in general for any random variable, not just for this problem. And so if you write that in, sort of expand out these in this like diagonal pattern, we see something really nice, right? So there's 1 p1, there's 2 p2s, we'll write them in a column. There's 3 p3s, we'll write them in a column. 4 p4s, 5 p5s, and so on. So right, you write down sort of these columns, you get triangles, and then if you sum the rows, you can see this is just p1 plus p2 plus p3 all the way up to whatever. This is actually always 1, right? This is any value, but you can write it as a probability that x is greater than or equal to 1. And then the second row is exactly the same, except there's no p1, right? We ran out of those. There was only 1. So this is the probability that x is greater than or equal to 2. And the third column is the same, or the third row is the same, except there's no more p2s because we ran out of those. We only had 2 of them. This is the probability that x is greater than or equal to 3, and so on. Right? Each row is the probability that x is greater than or equal to the next number. So the expected value of x is just the sum of probabilities that x is greater than something. And so this is a nice little formula, and it's actually going to be very convenient to solve this problem. Right? So what do we want in the problem? We want the expected maximum number of candies. So if we can figure out these kinds of probabilities, then we can, just sum these up to get the answer. So the probability that the maximum is bigger than some number, well, it's 1 minus the probability that the maximum is less than that number. And what does it mean for the maximum to be less? It means that everyone must have gotten less. So can we compute this? Yeah, so this one's actually pretty easy to compute. The probability that any one child gets less than a candies, well, there's a minus 1 possibilities for the number of candies they might have gotten, right? That's less than a. And there's k total possibilities how many candies they could have gotten. So the chance that any child gets less than a candies is a minus 1 over k. And for all of the children to get less than a candies, so they're all independent, right? So it's just the product. So it's just a minus 1 over k to the n. So the probability that the max is bigger than some number a is 1 minus a minus 1 to the k over k to the n. And the answer, we said, is just the sum of these. So it's just the sum for all possible values of a from 1 to k of a minus 1 over k to the n. Yeah, so that's actually the whole problem. This is going to be relatively simple once we sort of work it out. And this is the cool fact, I think, is, I don't know, it's not so useful. This is like a pretty specific situation, but it's neat, especially this sort of pyramid triangle, pictorial proof. Right, writing by columns and then summing by rows. So what's going on here? Let's actually code it up. As usual, probabilities, we will actually be using doubles. We said we had n and k. Yep. A equals 1. Okay, that's plus. That should be it, actually. Very short. right? It's literally just this formula. Pow is in CMath, I believe. We could actually also point our own pow if we wanted, but we'll just use the built-in one. So for 2 and 3, this was supposed to be 1 minus, right? Forgot about that. Okay, 2.444. Yes, we need to go down to the number of decimal places. Fix set precision 6, and we need IO_minute for that. All right. So that's the problem. Very short code, actually, but kind of a nice little math trick there. Nice break from the previous problem, which was quite nasty. So that's it.